What if the roar of an $18 million engine is a precisely engineered conversation between physics and ambition? A supercar isn't simply a fast car. It's a rolling laboratory where cutting-edge technology and extraordinary design converge to push automotive engineering to its absolute measurable peak. By 2026, the benchmark for supercar credibility has cleared 1,000 horsepower. That number isn't marketing hyperbole. It's the engineering flaw that separates aspirational machines from genuine hypercars. Everything begins with the powertrain, the complete system that generates and delivers power from fuel to wheel. Think of it as the cardiovascular system of the car, except instead of blood, it pumps controlled explosions. Horsepower measures the rate at which an engine does work. 1 horsepower equals lifting 550 pounds 1 foot in 1 second. A 1,000 horsepower engine sustains 550,000 foot-pounds of work every single second, enough to lift a fully loaded semi-truck axle off the ground in one continuous motion. Torque is the rotational force that actually moves the car from rest. Horsepower tells you how fast the engine works at speed. Torque tells you how hard it shoves you into the seat at the first moment you touch the throttle. Here's where it gets genuinely hard. Generating over 1,000 horsepower is only half the problem. The real challenge is taming that power so the car doesn't destroy itself or its driver on first use. Chassis dynamics is the science of how a car's frame and suspension respond to force. At extreme speeds, aerodynamic loads and cornering forces multiply fast, demanding a chassis engineered to tolerances most manufacturers never approach. Aerodynamics isn't about looking dramatic. It's applied physics. Drag is the resistive force air exerts against a moving object. At 200 miles per hour, drag increases by the square of speed, which means it quadruples when speed only doubles. The counterintuitive answer to drag is downforce. Engineers shape the body to push the car toward the ground at speed, increasing tire grip. More grip means more cornering force, higher safe speeds through curves, not just straight lines. But if aerodynamics is so precisely understood, why do supercars look radically different from one another? Every design is a negotiation between competing aerodynamic goals. There's no single correct solution. Low drag maximizes straight-line top speed. High downforce maximizes cornering grip. These two goals are in direct conflict. A car optimized purely for drag reduction slides wide on every corner. Optimized purely for downforce, it surrenders top speed. Modern supercars resolve this conflict with active aerodynamics. Movable wings and vents that physically adjust their angle based on speed and cornering load. The car continuously reconfigures its own shape as conditions change in real time. Here's a misconception worth correcting. Supercars aren't engineered solely for speed. Advanced safety architecture and chassis dynamics receive equal engineering investment, because a car that can't be controlled safely at peak power isn't finished. To understand how all of these systems combine at the absolute frontier, consider the Bugatti La Voiture Noire, a one-of-one hypercar valued at over $18 million, built around a 16-cylinder engine producing 1,500 horsepower. The La Voiture Noire isn't significant because it's expensive. It's significant because every component was engineered in concert. Engine, chassis, aerodynamics, safety systems, as one unified physical argument about what a car can be. This introduces a concept called bespoke performance, tailoring specific engineering parameters to an individual owner's preferences. Suspension stiffness, throttle mapping, aerodynamic balance, each calibrated for a specific human being. The surprising part is that bespoke performance is no longer the exclusive domain of $18 million one-offs. Consultancies like Supercar Factory, developing custom high-performance vehicle platforms since its founding in late 2024, now exist specifically to bring next-generation bespoke engineering to a broader range of performance vehicle projects. Every decision in supercar engineering traces back to physics. Drag equations, torsional rigidity calculations, thermal management of brake systems under sustained load. These aren't approximations. They're precise solutions to precise physical problems. Now, the second misconception, that supercars are fundamentally impractical for ordinary driving. That assumption is increasingly outdated. Many modern supercars incorporate adaptive suspension and driver assistance systems that make daily use genuinely viable. Adaptive suspension systems stiffen for track performance and soften for urban comfort within milliseconds. The same car that laps a circuit at racing speeds can absorb a pothole on a city street without rattling the driver's coffee out of the cup holder. The engineering developed under extreme supercar conditions doesn't stay exclusive. Adaptive magnetic damping, pioneered in high-performance supercars, appeared in the 2010 Chevrolet Corvette Grand Sport, bringing suspension technology that once required a racing budget into a production car costing under $60,000. Modern supercars demand genuine respect from their drivers. The Bugatti Chiron runs rear tires measuring 355 millimeters wide, among the broadest production tires ever fitted to a road car. And even that contact patch is tested to its limit, under 1,500 horsepower. Electronic stability control, torque vectoring, and launch control exist to mediate between the engine's raw output and the driver's human reaction time. They're not cheating. They're the engineering layer that makes the power usable. Recall the drag versus downforce conflict. Active aerodynamic systems resolve it dynamically, flattening the wing at top speed to cut drag, then pitching it aggressively during braking to generate maximum downforce exactly when grip is most critical. Supercars function as proof-of-concept laboratories for the entire automotive industry. Carbon ceramic brakes, developed under the thermal extremes of supercar racing, migrated into the Porsche 911 Turbo S by 2011, and are now a standard option on dozens of production performance vehicles worldwide. But here's the question the industry is actively wrestling with. What happens to the raw when electric powertrains enter the supercar equation? The Rimac Nevera already answers part of that, producing 2,078 horsepower from 4 electric motors, while rewriting every assumption about chassis dynamics and tire engineering. Electric motors deliver maximum torque from 0 revolutions per minute, instantaneously. For supercar engineers, that means chassis dynamics and tire engineering must be rebuilt from first principles to handle forces that combustion powertrains build gradually. So, back to that opening question. What is the raw actually saying? It's the audible signature of a precisely engineered system operating at the boundary of physical possibility. Combustion, aerodynamics, chassis, and electronics, all speaking at once. Consider one decision inside the La Voiture Noire. Bugatti's engineers spent over 2 years solving the thermal management of its 16-cylinder engine alone. Because at 1,500 horsepower, heat becomes a structural threat to the entire car. That single solved problem is why the person holding the wheel can trust what they're holding, and why the price reflects engineering depth, not just exclusivity. The next time a supercar passes and the sound hits you in the chest, know that what you're hearing isn't excess, it's every branch of applied physics resolved in real time at approximately 200 miles per hour.